Today, we are going to study hypothesis testing using the student t-distribution. In statistics, we often want to make a decision about a population. For example, we may want to know whether students in one class perform better than the national average, whether a new training method improves physical performance, or whether two groups have different mean values. But in real research, we usually do not have access to the whole population. We only collect data from a sample. Because of this, we need a method that helps us make a reasonable decision from limited sample data. This is where the t-distribution becomes very useful. On this slide, you can see two curves. One curve represents the standard normal distribution and the other represents the student t-distribution. They look similar, but they are not exactly the same. The t-distribution is usually a little wider, especially when the sample size is small. This wider shape tells us something important. When we estimate population information from a small sample, there is more uncertainty. The t distribution adjusts for that uncertainty. So, the main purpose of today's lesson is to understand when and how to use different types of t tests. Now, let us begin with the golden rule of the t distribution. In an ideal situation, we know the population standard deviation represented by sigma sigma. If we know the true population variance or standard deviation, we can use the standard normal distribution. But in real research, this is rarely the case. Most of the time, we do not know the true population variance. Instead, we estimate it from the sample data. This estimated standard deviation is represented by S. So the key difference is this. In theory, if sigma is known, we can use the normal distribution. In practice, when sigma is unknown and we estimate it using S, we use the student t distribution. The formula shown on this slide is for sample standard deviation. It measures how much the sample values vary around the sample mean. Because we are using an estimate instead of the true population value, our test statistic becomes less certain. That is why it follows a t distribution instead of a standard normal distribution. Another important point is degrees of freedom. For a one sample situation, degrees of freedom are usually n minus 1. This means if we have 25 observations, the degrees of freedom will be 24. So remember this simple idea. When the population standard deviation is unknown and we estimate it from the sample, we use the t distribution. This slide gives us a decision map for choosing the correct t-test. Many students become confused because there are several types of t-tests, but the decision is actually logical. The first question is, how many samples are we analyzing? If we have only one sample, then we use a one sample t-test. For example, we compare the average height of one group of students with a known population mean. If we have two samples, then we ask the second question, are the data points dependent or paired? If the data are paired, we use a paired t-test. For example, measuring the same person before and after training. The before value and after value belong to the same person, so they are connected. If the two samples are independent, we use an unpaired t-test. For example, comparing the test scores of two different classes or comparing two different groups of athletes. Then we ask one more question. Are the variances approximately equal? If the variances are approximately equal, we use the unpaired t-test with equal variance. This is also called the pooled variance t-test. If the variances are not equal, we use the unpaired t-test with unequal variance. This is often related to Welch's t-test. So the decision map is one sample t-test, two paired samples, paired t-test, two independent samples with equal variances, pooled unpaired t-test, two independent samples with unequal variances, unpaired t-test with unequal variance. This map is very important because choosing the wrong test can lead to a wrong statistical conclusion. Now we move to the first path. The one sample t-test is used when we want to compare the mean of one sample with a known or hypothesized population mean. The formula is t equals sample mean minus population mean divided by the standard error. Here the sample mean is represented by x bar, the population mean is represented by mu, the sample variance is represented by s square, the sample size is n. The denominator is the standard error of the mean. It tells us how much the sample mean is expected to vary from sample to sample. The logic is simple. The numerator measures the observed difference. The denominator measures the uncertainty or error. So the t value tells us how large the observed difference is compared to the expected sampling error. If the difference is large compared to the error, the t value becomes large. If the difference is small compared to the error, the t value becomes small. The degrees of freedom for this test are n minus 1. This test is very common when we want to check whether one sample is significantly different from a known standard value. Now let us look at an example. The scenario is about the height of 5-year-old boys. The known population mean is 100 centimeters. A teacher wants to test whether her 25 students are significantly taller. The hypotheses are null hypothesis mu equals 100. Alternative hypothesis mu is greater than 100. This is a one-tail test because we are specifically testing whether the students are taller, not just different. The sample size is 25. The sample mean is 105. The sample standard deviation is 18. Now we apply the formula. The difference between sample mean and population mean is 105 minus 100, which equals 5. The standard error is 18 divided by the square root of 25. The square root of 25 is 5. So the standard error is 18 divided by 5, which equals 3.6. Now the t value is 5 divided by 3.6, which gives approximately 1.3889. The degrees of freedom are 25 minus 1, which equals 24. The critical value shown on the slide is 1.7109. Now compare. 1.3889 is less than 1.7109 because the calculated t value is smaller than the critical value. We do not reject the null hypothesis. So the conclusion is at the 5% significance level, we do not have enough evidence to say that the true mean height is greater than 100 centimeters. This does not prove that the true mean is exactly 100. It simply means the sample evidence is not strong enough to reject the null hypothesis. Now we move from one sample to two samples. When we have two samples, the first major question is whether the samples are paired or unpaired. Paired data means that each value in one sample corresponds to a specific value in the other sample. For example, before and after training results from the same athletes. Left leg and right leg measurements from the same person. Pre-test and post-test scores from the same students. In these cases, the two values are connected. They belong to the same subject or matched pair. Unpaired data means that the two samples are independent. There is no direct one to one relationship between individual observations. For example, Group A and Group B are different students. Male athletes and female athletes are separate groups. Two different treatment groups are compared. In unpaired data, the sample sizes can also be different. So before choosing the formula, always ask, are these measurements from the same people or matched pairs? If yes, use paired t-test. If no, use unpaired t-test. Now let us discuss the paired t-test. The paired t-test is used when we have two dependent samples. Instead of comparing two separate means directly, we first calculate the difference between each pair. For example, suppose we measure a student before training and after training. For each student, we calculate after value minus before value. This gives us a new set of values called the differences. So the paired t-test transforms a two sample problem into a one sample problem. We are no longer directly analyzing the original two columns. We are analyzing the mean of the differences. The formula shown on the slide is t equals mean difference divided by the standard error of the differences. The mean difference is represented by d bar. The standard deviation of differences is represented by s. The sample size is n. The key question becomes, is the average difference significantly different from the hypothesized difference? In many cases, the hypothesized difference is zero. But sometimes, as we will see in the next example, the hypothesized difference can be another value. The paired t-test is powerful because it controls individual differences. Since each subject is compared with himself or herself, variability between people is reduced. Now we study a paired t-test example using train arrival delays. The company claims that trains arrive 3 minutes late on average. We want to test this claim against actual delay data. The null hypothesis is mu equals 3. The alternative hypothesis is mu is greater than 3. Here, the mean difference from the sample is 4 minutes. The standard deviation of differences is 3.8376. The sample size is 12. Now we calculate the t statistic. Observed mean difference minus claimed mean difference 4 minus 3, which equals 1. Then we divide by the standard error 3.8376 divided by the square root of 12. The calculated t value is approximately 0.9027. The critical value shown on the slide is 2.7181. Now compare the two values. 0.9027 is less than 2.7181. So we fail to reject the null hypothesis. This means that based on the sample data, we do not have enough evidence to say that the trains arrive more than 3 minutes late on average. Again, this does not mean the company's claim is absolutely true. It only means that the sample evidence is not strong enough to reject it. This example shows why statistical testing is not based only on the average difference. We also need to consider variability and sample size. Now we move to the unpaired t-test. When two groups are independent, we need to decide whether the variances of the two groups are approximately equal or clearly different. This slide shows two scenarios. In scenario A, the variances are approximately equal. In this case, we can combine the variance information from the two samples. This is called pooled variance. Pooled variance gives us a single stronger estimate of the common population variance. In scenario B, the variances are unequal. In this case, we should not combine them. Each group keeps its own variance in the formula. This is important because variance tells us how spread out the data are. If one group has very stable values and another group has highly scattered values, treating them as if they have the same variance may distort the result. So, for unpaired data, the major decision is, are the sample variances similar? If yes, use the pooled variance t test. If no, use the unequal variance method. This decision affects both the formula and the degrees of freedom. Now let us look at the unpaired t-test with equal variances. When the two sample variances are approximately equal, we use a pooled variance formula. The pooled variance formula combines the two sample variances into one common estimate. But it does not simply take an ordinary average. It uses a weighted average. Why weighted? Because a larger sample gives more information than a smaller sample. So the variance from the larger sample receives more weight. The formula uses ny minus 1 times sy squared plus n2 minus 1 times s2 squared. Then this is divided by ny plus n2 minus 2. That denominator is also the degrees of freedom for this test. After calculating pooled variance, we use the t-statistic formula. The numerator is the difference between the two sample means adjusted by the hypothesized difference between population means. In many cases, the hypothesized difference is 0. The denominator contains the pooled standard deviation multiplied by the square root of 1 over n1 plus 1 over n2. So again, the logic is the same: observed difference divided by estimated standard error. This is the central idea behind all t-tests. Now let us apply the pooled t-test to an example. The question is, do two energy drinks have the same caffeine content? The null hypothesis is mem1 minus mem2 equals 0. This means there is no difference between the mean caffeine contents of the two drinks. Drink 1 has sample size 7, drink 2 has sample size 5. The sample mean for drink 1 is 30.0086. The sample mean for drink 2 is 31.6980. The sample variances are also given. Because the variances are considered similar, we pull them together. The pooled standard deviation is shown as 1.1995. Now we calculate the t-value. The numerator is 30.0086 minus 31.6980. This gives a negative difference because the mean of drink 1 is smaller than the mean of drink 2. Then we divide by the pooled standard error. The calculated t-value is approximately minus 2.4052. The degrees of freedom are 7 plus 5 minus 2, which equals 10. Now, when interpreting this result, we need to compare the calculated t-value with the critical value or use a p-value. The important point is that the negative sign only tells us the direction of the difference. It means drink 1 has a lower sample mean than drink 2. For significance, we usually consider the magnitude of the t-value and compare it with the critical value based on the selected significance level. Now we discuss the unpaired t-test when variances are unequal. This is often called Welch's t-test. Here, we do not pool the variances. Instead, the variance of each group stays separate in the denominator. The denominator contains s1 squared divided by n1 plus s2 squared divided by n2. This is important because each group contributes its own uncertainty. If one group has a large variance, that group should influence the standard error differently from the other group. The numerator is still the difference between sample means adjusted by the hypothesized population mean difference. The main difference is in the denominator and the degrees of freedom. For equal variance, the degrees of freedom are simple: n1 plus n2 minus 2. But for unequal variance, the degrees of freedom require Welch's approximation. The formula looks complicated, but the idea is simple. Because we are not pooling the data, we need a more careful estimate of the degrees of freedom. For teaching purposes, students do not always need to memorize this long formula immediately, but they must understand the logic. Separate variances mean separate denominators, and separate denominators require adjusted degrees of freedom. This final slide summarizes everything we learned today. There are four main t-test situations. First, the one sample t-test. Use this when we compare one sample mean with a population mean. The degrees of freedom are n minus 1. Second, the paired t-test. Use this when we have two dependent samples, such as before and after measurements. We first calculate the differences, then test the mean difference. The degrees of freedom are also n minus 1. Third, the unpaired t-test with equal variance. Use this when we compare two independent groups and their variances are approximately equal. Here we use pooled variance. The degrees of freedom are n1 plus n2 minus 2. Fourth, the unpaired t-test with unequal variance. Use this when the two groups are independent but their variances are not equal. Here we do not pool the variance. We use Welch's approximation for degrees of freedom. Now let us close with the most important idea. Although these tests look different, they all follow the same basic pattern. We take an observed difference and divide it by an estimated standard error. That is the heart of the t-test. So whenever you see a t-test formula, ask yourself three questions. What difference am I testing? How much uncertainty is there in that difference? Which degrees of freedom should I use? If you can answer these three questions, you can understand and apply t-test correctly. In research, the t-test is not just a formula, it is a decision making tool. It helps us decide whether an observed difference is likely meaningful or whether it may have occurred simply because of sampling variation. That is why understanding the t distribution is very important in statistics, research methodology, biomechanics, psychology, education, medicine, and many other fields.